Hi and welcome to this session on bare metal programming. So without further ado, uh, this session is meant for people who want to understand the fundamentals. Okay, so I would recommend go through this video one time, two time, three time, as many as times as possible till you get the essence of what I'm trying to say. Okay, and for your convenience, I have provided the GitHub session. Okay, and we have all the code that we are going to do here, and we are also going to cover a bit of assembly, and we also have the textbook or the notes. Okay, it's like 20 pages long, shouldn't take more than 5 minutes to read. It was compiled on December 14th. Okay, so let's get to the whiteboard and let us start. So what is a bare metal project? Okay, what do you mean when you say it's a bare metal project? A bare metal project is basically how close you are to the silicon. If you take a chip, you have different way of programming that you are already aware of, like Arduino or HAL or I don't know, whatever, MicroPython or the ESP-IDF. So all these are ways that you can write or compile code that will then interact with the hardware. So bare metal is the lowest level of code that you can write, okay, and get it to execute. It has its advantages that you will be exposed to the maximum capabilities of the hardware. You will have know-how, and doing bare metal on a new peripheral is usual exercise in understanding how the peripheral works. Okay, so it can really put you in the zone. So my recommendation is, when you think of bare metal, you think of like you are in control, you have direct hardware access, you write all your files, you have minimal memory footprint, and you have full control over the startup. All right. So there are people define bare metal differently, but for me, this is how I would put it. All right. So as long as I have direct access to the registers and I'm not using any CMSIS libraries or any vendor provided libraries, I would consider myself to be working in the bare metal mode. Okay, that's my definition. So this bare metal term is relative. So let us stick to one definition. Okay. So let us understand what are the different levels of abstraction. Abstraction means hiding. Okay. So when you don't want to directly work with something and a function or an interface is provided to work with that peripheral, that concept is called abstraction. At the register level and bare metal level, there is no abstraction except the C functions that you write. Okay. Now, ARM provides the Cortex microcontroller software interface standard (CMSIS) helper functions to access the peripheral and interrupt definitions. We will see what it is. So if you generate an empty CubeMX project, you will have access to this. But we will be not using CMSIS today. And we will also not be using any hardware abstraction layers. So it will be pure bare metal. All right. So without further ado, let us get started and let us understand the anatomy of a bare metal project. Okay. So when you really say that I want to work with bare metal, what you mean is you have a startup file. Okay. And guys, internalize this slide. A startup file contains the vector table, which is the most critical part. We will come to what a vector table is, but it is an area in memory that has the end of stack, and it has the pointers to the addresses of all your interrupt handlers. It's very important to remember in ARM or RISC-V. Any modern architecture your startup file would define your vector table first. All right. And next, memory initialization. Basically, the startup file also copies the flash data to RAM. It boots up the microcontroller. Okay. Next, you initialize your stack pointer, and then you have the assembly code needed to jump to the entry point, which is the start of the program. Generally, this is the reset handler, but we will study the startup file and we will arrive at that conclusion. All right. We will optionally write a minimal startup file required, and then we would see how small an assembly program we can write, and then we will move on to C. Then comes the linker. So the linker really tells you how to partition your memory, or if you have multiple applications sharing the flash like a bootloader and an application, your linker file is where you would define the start and end addresses, and also certain sections in memory where you want your variables to reside. This is not so much important for now because we are not partitioning our memory or creating regions within our memory, but it's good to know what it does. And we can also write a minimal linker file that does all this. All right. So a linker file defines where to put your code and data in memory, how much memory is available, and what order the section should be in. All right. Next is your main.c. It can be single or a multiple C and .h headers. Okay. Or you can just do it purely in assembly. It's up to you. And then optionally you have a make file. See, when you have multiple files in your C compilation, you can organize your compilation using a make file. A make file is basically interface to the GNU make tool. Okay, it is a script. Make file is a script to the make tool that tells you what is the order of compilation and linking. All right. So we will understand and orchestrate, and we are going to build a bare metal project right now, and we will also see the debug setup and how we are going to program and test it. All right. So I assume at the very minimum you have a STM32 Blue Pill, you have a JTAG or a JLink or a ST-Link debugger. Okay, and your connections are proper and you're able to detect your chip in your debugger. That's the bare minimum. So in the next section we will create our basic bare minimum bare metal program. We'll go through it and we'll understand. All right. Okay, now we are going to cover the tools that are required to build and flash our programs. Okay, we are not going to use any proprietary IDEs, but we are going to use the XPack tools that are provided from the open source. The first is our compiler, which you will get from the XPack series. Okay, so I have downloaded for Linux, but the same package is available for Windows. So if you go to the XPack releases, the release page, so you can check out the Windows version. Okay, so this is a release for Windows, so you can check it out. It comes in a zip package, so you have to show all the 14 assets, and if you go down, Win32 here. Okay, so this is the Win32 package, that is the compiler. I'm using the Linux version. All right. Similarly for OpenOCD, OpenOCD is the flashing and debugging tool. Okay, it stands for Open On Chip Debugger. We can have a session on it separately. If you just want to flash and check, there are other tools available like your ST-Link utility, but for debugging and stepping, this is absolutely essential. Okay, so once we have this, we can load up our project, and then we can build using the ARM compiler, and then we can flash using the OpenOCD tool. So it is essential that you have these two tools before downloading the source and building the projects. All right. Now let us check whether our downloaded applications work, and we can start setting up the path for them. Okay. If you don't set up a path, your make file will become complex. So in Windows, you can add these to the path variable, but on Linux, you can alias them. Okay. We are not going to do that, but we are just going to see in this section how to just check if our compiler works. All right. So the way we are going to do that is we are going to go to this directory and check for the bin folder. This is where the ARM binaries are. And a compiler is not just one tool. The GCC is a ARM GNU compiler collection. So there are other tools like the linker, the map file generator, then you have your NM tool, your object dump tool, then you have your debugger, which is the GDB, the GNU debugger, and the open on-chip debugger will create a remote session for you to connect to this debugger. Okay, that is how debugging in IDEs work using the GDB. Okay, so you have your profiler, and it's a collection of tools, okay, that also tell you the size of your binary and help you write a better program. So remember, it is a collection of tools, but for the compilation and assembly, we just need two tools, which is the GCC and the AS. AS is the assembler. Okay, so how do we check if this works? So just we'll open a terminal into this directory. On Windows, you can do the same on Windows 11. Else, you open a command prompt and go to this directory. Okay, we'll open a terminal. Hope my font size is visible for you. Okay, so once we are in this directory, let me do a quick ls and understand. Then let me go to bin. On Windows, it'll be the same. Okay, so once I'm inside the bin directory, so I can drag and drop this tool. Can do the same on Windows, and it should say fatal error, no input files. It means it works. Or you can say -v for version. So it gives a lot of output, but basically you can verify whether this is the version that you have downloaded. Okay, so now we are going to check if whether our OpenOCD works. Similarly, we are going to the OpenOCD directory, we are going to the bin directory, and we are going to drag and drop. Right, it works, but it is unable to connect to anything. So in the upcoming section, we are going to use the compiler and the OpenOCD tool to build and flash our programs. And we have also verified that the both tools have been downloaded successfully and they work. Now that we have our tool set up, guys, we can start writing our startup file, linker, main, and make file one by one. Okay, so let us understand what this vector table is. Okay, and what the memory initialization is. Okay, so basically, if you open the notes, okay, so we will have the definition of the vector table. Okay, here. So your vector table is nothing but your stack pointer end, your reset handler, and a collection of all other interrupts. I have removed those, and I'm just saying to set up the stack and the reset handler. This is the minimum code you can write, right? So this syntax is in assembly. Okay, so the way we are going to do this is we are going to create a file called startup.s, where we are going to write this code. This code is present in the minimal project, not the minimal project with C, the minimal project within the Baremetal GitHub repository. We are going to click it and we are going to the startup.cs. Okay. So if we study the contents, first we are saying that I am using the unified syntax. So we have our ARM instruction set, okay, thumb. So, and there are other ways of writing the ARM assembly. Here I'm using the ARM unified syntax. You can refer this later, but for the interest of time, let us understand that this is the way I'm setting up the startup file. I am going with the unified syntax. Then my CPU is ARM Cortex-M3 because I'm using STM32F103. If you are using a different CPU like M4, please make changes accordingly, or an M0. And then I am not using my FPU. Instead, my floating point will be done in software. So floating point is IEEE 754, I believe. So that is how you implement um, your decimal numbers or your mantissa. So numbers like 10.102. So this you can do with floating point units. And next you have your sub instruction set, which are limiting to the thumb. Okay, so you should understand that an instruction set is the number of possible mnemonics that the CPU can access or execute. Mnemonic is nothing but an operational code. So different CPUs have different instruction set, and this particular CPU we are limiting it to the thumb instruction set. Now what this instruction set is in detail you can go to the notes, but for now just understand that we are sticking to the thumb instruction set. Next we are going to declare our global vector table and our global reset handlers. This dot global are nothing but regions in memory. Okay, and then we are going to start our flash section. Okay, in our flash section we have an ISR vector, and this alignment is basically to bring the 8-bit alignment. Okay, because your startup code will sit in flash, right? And your flash is partitioned into 8 byte segments. So your alignment 2 is helpful to complete this entire line into 8 bytes. Okay. Next, in your section, you're starting your vector table after your alignment. So first is you are going to introduce the variable called eStack. These dot words are nothing but variables, global variables. Okay. eStack is nothing but the end of stack. And next you have your reset handler. Your reset handler is the point of entry when you press the physical reset button on your STM32 device, on your microcontroller board. Okay. And here in this section, dot text is where the code resides. Okay. So this ISR vector is the vector table section, and this is the code section. Okay. Here we are telling that my reset handler will load the eStack variable into register 0, and then I'm going to move the contents of my register 0 into the stack pointer. Basically, I'm setting up the stack pointer, and then I'm going into a loop, a basically while loop, infinite loop, where I'm moving the value ABCD hexadecimal into the register 3, and I'm continuously looping. This is the minimum program I'm going to write. If you didn't understand, just go through the video again. This is where I am declaring my startup file, and this is the only program that is going to fit. This is the minimum program that you can run on your microcontroller. You set up your vector table, you set up your reset handler, and in your vector table you define your stack, and then in your reset handler you tell where your stack pointer is, and then you move your stack pointer, and then you can set up an infinite loop so the program doesn't crash. So it just keeps repeating once it enters here into this while loop infinitely. We are going to build this file, we are going to flash, and then we are going to see the behavior of this. More information, please find the attached document. Okay, but the documentation is more elaborate, and it will also cover things that we cannot cover in a YouTube session like this. Okay. Now we are going to build our startup file. I've already downloaded the source. Okay. Here. And now we are going to build this. Okay. The way to build this is if you go to the readme.md, I've already given the complete assembling instruction. Okay. How to assemble this startup file. And it is going to generate a pair of files, which is the linker and the elf. Sorry, the map and the elf. I've also written the linker, the bare minimum linker, and the way this linker is written is I'm simply telling that my entire flash size is 64 kilobytes and starting at this address. My RAM is 20 kilobytes and starting at this address. And my end of stack is my origin of RAM plus length of RAM. Where do I get this information? It is generally available in the datasheet. Okay, so STM32 generally their flash starts at this address, and then here you mention the length of flash. Okay, so that's it. That is all there to the linker file, and this e-stack variable, since we have already mentioned in our startup file as a .word e-stack, it will be available to the linker also during compilation, because we are going to submit our linker description to the compilation. This is the compilation command. So I'm just directly going to copy this. You can modify the path according to your download. In Windows, there'll be some path in .exe, and afterwards everything will remain the same. Maybe you have to set the path of your startup file. Okay, I cannot account for every system, but I can show you how it works on my system, right? Clear this, and I will go to the terminal, or I'll open a terminal here. I'm going to increase the font size so you can see I have copied the command, and I'm going to paste it in the terminal. All right. There's no output, but we can go and observe the two files that are being built. Okay. So if I go by detail, last modified, they have been just modified, these files, the elf and the map file. If we open the map file, we can see where the flash sections are. All right. And there is nothing much. There's no data, nothing. It's very simple. Okay. And we can also see the associated .elf file that we are going to flash. Okay. How do we flash? We are going to invoke the OpenOCD session. That OpenOCD session command is present in the README. Okay. So this will simply open the OpenOCD session. It won't flash. If we want to flash, we have to also mention the flashing commands. Okay. I've provided a launch.json to work with Visual Studio, but that will be a bit complex for now. So the way OpenOCD works is we first give the path to the OpenOCD binary, and then we give a path to the OpenOCD interface. In this case, I'm using ST-Link v2. So this is a path to the OpenOCD interface. And then we give path to the configuration file. So two paths. So I can ideally put it like this. So first we need the path to the OpenOCD. Next we need path to the configuration file of the debugger, which is ST-Link. And we need the path to the target, which is the STM32. Okay. So I'm going to copy this. I'm going to run this. Okay. So it says command not found because I have split the lines. Let me put it back. Not splitting the lines now. Copy and run the command again. Let me clear all this nonsense. Control Shift V. It has successfully connected to the STM32 F103. It has detected my chip ID and then it is waiting for a debugger connection. Once I have this, I can open Visual Studio or any GDB debugger, connect to this and debug the code. Alright, in the upcoming segment, we are going to see how to debug this. Okay. Okay. So I made a little modifications so that we can better see the startup behavior. Okay. So one is the adding some dummy data and shifting the reset handler by one word, that is 4 bytes, so that when the jump happens we will be able to catch it in our debugger. Now you should be familiar with debugger if you have worked with C. Okay, but for now let us open the readme file and begin the compilation. In the compilation you will see that I am invoking the assembler. I am using the -g flag for enabling debug symbols. I am not using any optimization. My input is my startup file only. I am using the thumb instruction set with the Cortex-M3. All warnings are enabled and I am passing my linker file. And in the linker file also I have made some changes, little changes to have the vector table and the text section. Okay. This is just to see and catch that output in the debugger. Okay. And I have passed no std library because generally if you're using C, it will expect the standard library to be present. Optionally, I am generating a map file and my final output will be a .elf file. Okay. Now, this is the command to compile. Let us copy and let us paste. We have compiled. Now, this is the command to flash. Okay. Go through the OpenOCD command. It clearly gives you the configuration for everything. Okay. And then the OpenOCD directive is to program the ELF file, verify the contents, reset the microcontroller, and then exit the session. Okay, so we are going to do that now. That's it. So the programming happened, the verification happened, and we have resetted the target. Now, in order to capture the breakpoint in the Visual Studio, I have created a minimal launch.json. Okay, so this launch.json is provided to you as part of the GitHub repository. Now, what we are going to do is we are going back to the README file and we are going to start the target session. Now, in the target session, we'll allow the GDB debugger to connect to the running program on the microcontroller and then start the debug process. Okay, so now you can see I have started the debug session and it is listening at port 333 for GDB connections. Now, since my launch.json is set up, I can go to my startup file and then I can run and start my debugging. I have placed 2 breakpoints and look at it. The first breakpoint will come at the reset handler. Okay. Now here I can watch for my registers using the dollar symbol R0. Okay. And similarly R3 dollar R3. So right now R3 is pointing elsewhere, but if I run and go through the loop, you can see that as the loop progresses, my R3 variable is being filled with ABCD and I can never exit this loop unless I reset my controller. So this is the bare minimum startup code that you need to get, and we also got something usable by playing around with the registers. In the upcoming segment, we are going to inject C code, okay, a main.c, and we are going to toggle the onboard LED at PC13. All right. If you don't follow this, please go back and visit the session or go and visit the documentation. Okay, this will be much clearer. Generally, nobody goes to this level and edits the startup file, but this is just for our understanding. All right. Okay guys, so here we have our physical setup. So this is our debugger ST-Link. We have our microcontroller and this is a UART. This is optional. I'm not using it. But this LED you see, this is the PC13 LED. We are going to blink this via our main program that we are going to attach. Okay, so the way we are going to accomplish is by writing a make file. Okay, so this is the make file. A make file specifies the tool chain, the tools that are needed to build and link the file, the name of the final program, and the sources, the startup.s and the main.c. I am also specifying my compilation to include all the debug information, both from the C and the assembly. I am sticking to the thumb instruction set, and also I am specifying my OpenOCD configuration. Your debugger and your microcontroller code might vary, so you might have to change something here, but overall this is the flow. Okay, if you follow my make file, you should be able to do something like this. Okay, you can do make clean to clear out, make to build your application and see how much size it is taking. Here my program is taking 96 bytes. Yes, 96 bytes. Okay, and now we can also see the memory using the elf ripper. Okay, for that we need to inject data once the build is done by giving the elf and map path. Okay, this is an extension that you need to give. Let me give the elf path and let me give the map path. Okay, and let me process the data and we can see what exactly is sitting in RAM. Okay, 96 bytes. Okay, nice. Now let us go back to the terminal and actually flash it. So using make flash, we can flash our microcontroller, and then using make debug, we can start our debug session. Okay, now just quick intro into the code. Okay, so let me go back to our diagram. Okay, and let us understand what is going to happen when we execute the code. First, the microcontroller is going to power on and search for the vector table at this address, and then it is going to set the stack pointer from the first word, and then immediately after that it is going to search for the reset handler. Okay, in our reset handler we are going to copy the data and memory, okay, into the RAM from the flash. Okay, this is a sequence diagram. So from the flash memory we are going to copy data into the RAM memory, and once that is done we are immediately going to call the main function. This main function is not in the startup file assembly, but this main function is present in the .c file. Okay, here. So you can see the main function in this startup code is being called here. It is actually linking to the C function. Okay, and this linker is handling the data. Okay, so the linker is clearly telling where the section should sit, and this is the minimum linker file that allows you to do this. Okay, so that is enough explanation. Okay, so we have got this data from the memory map peripherals from the datasheet. So if you open the STM32 datasheet, you will have a memory map on page number 34. So I know where my flash memory is sitting, where my RAM memory is sitting, and also where my GPIO port C is there. Remember, my LED is on PC13, port C13. Alright, and if I go into the reference manual, okay, let me see this one. It's the reference manual. we can also know where the exact registers are. Okay, this is the register map for CAN peripheral, but I am looking for the GPIO peripheral here. General purpose register, functional definition, register map. So I will explain the GPIO peripheral later, but for now we need to understand that for pin 13 we need to set the control bits, okay, and then we need to set the out direction register, okay. So this is for the lower ports and this for the higher. PC13 happens to be in the higher region because it is 13, so we need to add the fifth bit here because 8 plus 5, okay. Again, we will cover GPIO in a later segment, but for now we need to understand how to read data sheets, okay. So take this for granted, whatever code I am giving. This code will set up the peripheral at PC13 as output, okay. We will come to the GPIO peripheral later. This is just setting up our project for future expansion, okay. Now using the C bit manipulation commands, we are able to set up the GPIO-C clock. We are able to set it as the output in the configuration, okay, CRH configuration register here. And if we want to toggle it on or off, we are going to use the out direction register here. And then we are going to generate a delay using a for loop. This is going to waste CPU cycles. I don't like to do this, but in the future we might use a timer peripheral and get this done, okay. Sounds exciting? So generally we need a data sheet and a reference manual and a general understanding how the bare metal works, okay. I have placed my breakpoint inside while. Let me switch back to the camera mode and just expand this, and you can see it is already blinking. So let me just initiate my debugging, okay. It has come at the startup file. Let me start and continue. On, off, on. So this is the toggling behavior, and this is the bare metal, okay, minimum project you can set up. In the upcoming segments or problem videos, we are going to discuss each peripheral one by one, and probably we might start with the GPIO peripheral. All right, thank you.